We'll get started here in just a second. The equipment is still being set up. While we're waiting, anybody have any questions on what we've done so far, or any questions about anybody tried to go to the TM office hours yet? Yeah. Are they being helpful? I don't know who said yeah. Yes, no?
Yeah, so I have a question about validation in the cross validation set.
Uh-huh.
I'm trying to understand the reasoning for that when we already have a test set.
Because you're using them for different things, right? So when you originally split off the test set, that's for estimating the generalization error of your model. Okay. When you do the cross-validation, you're going to have a whole bunch of folds, and each fold can represent, or can be its own validation set, or is used as a validation set. There, you're like choosing hyperparameters. So you don't want to choose hyperparameters on the same set that you estimate generalization error. You're mixing up the two, right? Like what you're doing there is you're overfitting. If you don't do that, if you just like pick your hyperparameters on the test set and then use that to estimate how well you're doing, you're overfitting to the test set, right? So this is a way of preventing yourself from overfitting on the test set. So overfitting on the training set is overfitting on the first kind, overfitting on the test set is overfitting on the second kind. And that's why you're just trying to prevent that.
So during that, we split it up into 5 parts and we take one as validation. So
You split up the 5 parts, and then, so if you take the first part, you're going to train 5 different models. Where, for the first model, you're going to take the first part, and that's your validation set, and the other 4 parts you train on. And you validate on that first one. And then you do it again, but you train on the first, third, fourth, and fifth parts, and validate on the second, and you do it over and over again. It's a way of kind of like extending the size, like the amount of data in the training set. I mean, you could just do it on one fold and get some sort of estimation, but it's sort of most helpful to split it up that way when doing hyperparameter tuning, because it just gives you like a better, gives you a better sense of how the hyperparameters will behave Yeah, because like every time you sample down, you're introducing more error into your estimate of error on the training or on the validation set, because it's like you train on something smaller. So like every time you reduce the size, your estimate's becoming more noisy. So you do this kind of like 5 times or 3 times or however many times you do it, just to give yourself kind of a better sense of what the true error is on those for that choice of hyperparameters. Cool, good question. Okay, well, let's get started. So, so far we've done no neural networks really. We're getting there, almost there. We've been building up some of the basic ideas of what we're going to be using when we actually get into doing convolutional neural networks. Well, doing deep learning of all kinds. In particular, we'll start with convolutional networks very soon. But you know, we talked about ideas of score functions using very simple ones like these linear functions, finding our loss at each data point, averaging these losses over all our data set to get some estimate of the overall loss in our data set. Again, like some notion, some measure of how well or poorly we're doing on a particular task. And we also talk about regularization and adding that in, and you know, using that to get something out of our weights, impose some sort of structure or behavior in our weights. Usually that's to prevent overfitting. We talked about how these loss services, when we start to have kind of more complicated functions, these loss services become very bad for optimization. They have lots of local minima. And we talked about how to use gradient descent to kind of get ourselves into one of these local minima. And we talked last time about stochastic gradient descent, where we don't estimate the gradient of our loss function using all the data points. We just use a small sample of the data points and estimate it from that. And that we do that like primarily for numerical reasons, for computational reasons. Like it's just you can't on GPUs you can't hold that much. Like you know, if there are images, these big images, you can't hold that many images in memory. But it also turns out that it acts as a regularization to do this, because it gives you a little more noise in the random walk you're taking on the loss surface, which ends up being beneficial. And some of you have come to me after class and said, how does this even work? And again, I don't really know why it even works. Like why it is that we can go to, like, we can basically start pretty much anywhere in the loss surface. That's not true. We need to actually start with weights that satisfy certain statistical properties, and we'll talk about those as we get to those topics throughout this class. But it turns out that we will often converge to, it'll be different minima in the loss surface, but like the overall behavior in the model will be the same. It'll be about the same loss, and that will translate to about the same accuracy, or whatever measure we're using to see how well we're doing.
I have a question, hopefully, if it's derailing the conversation, feel free to skip it. But I was wondering if in the mini batch sampling, if you're trying to get in like an even number of the classes across it, or does it not matter?
You can definitely try to do that, but it turns out doesn't matter too much. I mean, you don't want the batches to be you don't want everything to be of the same class or like be highly correlated batch. You usually don't get that when you're doing random sampling. If you have a really imbalanced problem, you want to deal with that. You probably won't deal with it at the mini batch level. You'll deal with it like how you weight, like how you sample the data itself. But yeah, typically you just want to make sure it's just mostly random. Okay. Other questions? Oh yeah, go ahead.
What are the sizes of the batch? I mean, on what basis we are deciding how much one batch should consist of? How many samples should be?
It's a hyperparameter like all the other hyperparameters.
So just randomly we have to.
You know, it's not random. You usually start with something that makes sense, and like we briefly touched on last time. You know, the batch and the learning rate are related to each other, especially if you're using stochastic gradient descent. And so, you know, whatever batch you pick, that's going to sort of, like whatever batch size you pick, that's going to sort of dictate what learning rate you're going to need to kind of get decent. training dynamic, uses performance, but it's definitely not random, but it's also, there's not like an a priori, like, here's what my data problem, now I know what learning rate to pick. It's a hyperparameter, you're gonna have to tune it. There's definitely like lots of heuristics for like how you start with these things, Andrew Karpathy, who's head of machine learning at Tesla, has a great blog post on like how he starts his neural network training, and actually something that everybody should probably read in here if you're gonna get serious about training neural networks. And he has like a favorite learning rate that he always starts with. And, it doesn't mean it's gonna work for you, but it's like he starts with that. It's like it's 3 times 10 to the negative 4 or something. But yeah, it's heavily problem dependent, so you're not going to know before. Okay, so we started talking about back propagation last time, and we're going to continue talking about that today. This is like the key algorithm for training neural networks or any differentiable loss function, where meaning that the loss function is differentiable function of its weights or its parameters, and it's just like we talked last time. It's just many applications of the chain rule in basic calculus. So remember, we started talking about computation graphs. This is just like one node in a computation graph. You have in this very simple setup, we've got 2 inputs to some computation f and 1 output from there. So x and y are inputs, and z is the output of it at this node. And the way that propagation works is, again, maybe let me just say this. I don't know if I'm not sure how much I kind of pointed this out. Let me just point this out right here. So, like, what exactly? We definitely pointed it out. But let me just sort of state it one more time. So, what's this whole back propagation thing about? Well, remember what we're doing. We have a loss function that tells us how much loss we have at whatever point in the parameter space we're at, right? So, whatever our parameters are, we have some sort of value for it. We're able to calculate the loss there. That gives us some value of the loss. It's a whole surface. We're trying to get to some minimum in that surface. So, there's lots of ways to think about how to get to that minimum. The method we're using of stochastic gradient descent is basically just walking down the gradient, which is locally it's giving us the direction of steepest descent. And so to be able to do this, we need to keep calculating over and over again, the loss and its gradient at every place that we end up with in parameter space. And so this whole algorithm is about how to calculate that gradient, how to calculate it with respect to the weights. And we need to do this over and over. So like for every single mini batch, we need to we calculate the loss in the forward pass, but we also need to calculate the gradient of each of the components, so each of the losses in that for each data point in that mini batch, and then we just do that over and over and over. Like this is training a neural network. This is what we're doing. We're just doing this. We're doing this thing over and over and over and over. So we need to be fast. It turns out this is a very fast algorithm, mainly because we use very simple, not super simple, but simple enough functions in all the definitions, all the computation nodes, so that these gradients are easily calculated. So remember, this is all just about so every time we get one of these gradient, we calculate these gradients, we update our weights, move to a new point in parameter space, we just keep doing it. So, and then eventually it converges to something, and that's what we're happy with. So the reason we're spending so much time on this is the core of what we'll be doing, like how you will train neural networks. There's variants of stochastic gradient descent. We'll talk about those at some point, but this is the core of it. So the way this works, the way that you get information about the gradient through this node is we do it backwards. We start from the end of the computation, the output of computation, and work our way back to the beginning. And so the way that this works is that at any node in our computation, we can calculate the local gradients, the output with respect to the immediate inputs. So the immediate output with respect to the immediate inputs. So z with respect to x and with respect to y here. And then, we're just accumulating, through this algorithm, we're just kind of accumulating gradients as we go so that like at this step in the process, we know what the partial derivative of our loss is with respect to z, which is our output here. We want to back propagate that information now to what the loss, what the partial derivative of the loss is with respect to the inputs now here, x and y. And we just keep pushing it backwards till we're back to the weights. So that's just an application of the chain rule. The partial derivative of the loss with respect to x is just the partial derivative of the loss with respect to z, the output here, and then the partial derivative of the output z with respect to x. And those just multiply together because of the chain rule. And same thing for, I'll just replace x, or for y, just replace x with y. So super nice. Multiplications are easy to do. Most derivatives are pretty easy to do. All the frameworks that we use just kind of keep these. They just know what these are, and they quickly calculate these things. Okay, that's back propagation. So let's do some. Yeah, let's just propagate back to other nodes. So let's go through another example of how this works. A little more complicated. So here's our function up here. This is something that we will, a function that we'll be more likely to see as we start training neural networks. This kind of sigmoid function here. It's got a vector of 3 weights, W0, W1, W2. W2 is a bias, W1, or W0 and W1 are coefficients in this linear combination. And our input is just, in this case, 2-dimensional, x0 and x1. And then it's just put all together in this, somewhat, not too complicated, but somewhat complicated way, right? So the way that this computation graph works here is, how do we build up this computation here? Well, we start from the inputs and our weights. They're the first components of this computation. So we need to multiply W0, X0. So W0, X0 is a branch. Those two branches come together in a multiplication. Same thing with W1 and X1, another multiplication. And then W2 eventually gets added to all of those. The output, the products of these things get added together. And then the sum of those things gets added to W2. That all gets multiplied by -1. That's what that -1 is in the exponent. Then we exponentiate that. Then we add 1 to that. And then we take the reciprocal, just flip it up into the denominator. So each one of these steps is a way, like you're composing all of these different functions together to get the final output. And since we have composition of functions, we are in chain rule land, and we're using back propagation here. So this has already picked values for the weights and for the inputs. Simple ones so we can do some of the math here. So the weights are 2, -3, and -3. And the input, x0 is -1, x1 is -2. And then just all the computations computed all the way forward. So that's called the forward pass, going from the inputs all the way through to the output. Okay. So let's send this back now from the end through back to the weights and the input. Okay, so here at the end, this is always, if you think of this as the output f or z or whatever, we're always starting with the partial of f with respect to f, or the partial of z with respect to z, whatever. It's always 1. We always start with 1 there at the end. Remember, green is the result of the forward pass, red's going to be the result of the backward pass. So the starting point is always this 1. That partial of the loss, you might think of it like in the analogy making of the loss with respect to itself. Okay, so now we're going to start working backwards. So, so how are we going to get the value that goes right here? What do we need to do next? We have the upstream gradient. It's just 1. This red value here, 1, and we need to multiply that to the local gradient of that particular function, 1 over x, and evaluate it at the particular value of x, or the input here, which is 1.37. So, what's the derivative of 1 over x? Yeah, it's on there. Just like that calculus book that you once bought, it was like $150. The only thing you needed from it was the inside of the covers, you know, it had all these things. Yeah, so that's our derivative. So our local derivative is, you know, -1 over the square of 1.37, which ends up being some number I don't have on here, but I do have it on there because then we multiply by 1, so it's minus 0.53. So this is the upstream gradient, 1. This is the local gradient evaluated at the particular value of the input. Multiply those together, those are the two partials, and now we have minus 0.53 as now like the upstream gradient as we work back to the next node in the computation graph. Next one's pretty easy, adding 1. What's the derivative there? Well, it is 0, but we're adding 1 to the, that's kind of a bad way to write this maybe. It should be like x plus 1. We're adding 1 to the input, right? So the derivative is not just 0. That would end this thing altogether, be 0 all the way back, right? But it's, you know, it's x plus 1. So the derivative there is just a 1. The local gradient here evaluated at 0.37, but it's a 1's constant, so it doesn't know anything about 0.37. Then again, multiplied by the upstream gradient, in this case, minus 0.53, and we get again minus 0.53. And this is super fun, right? So we just gonna keep doing this. Nice thing is, like all the gradients, all the derivatives that we're calculating are pretty simple, right? So we've got an e to the x here. That's just itself again. So we calculate the gradient, so we calculate the derivative here, it's just e to the x, we evaluate that at the input, minus 1, that is our local gradient, times the upstream gradient, we get back minus 0.2. Pretty simple, right? This just continues. What's this one going to be? This is multiplying by minus 1. So what's our local gradient going to be? Minus 1, exactly. Right, like it's this rule right here. So our constant here is just minus 1. So that's the upstream, that's the local gradient. And then our upstream gradient is minus 0.2. So what do we need to get out? Look at you guys. You guys could have invented that problem. You know, this was first published in like 1980. I can't remember which year, 1983 or something like that. So it's old. So it's like neural networks is based on really old stuff. Actually, it's only because we have like some way of doing all these computations really fast now and storing a lot of data and being available that like neural networks have become a thing. It used to be if neural networks were on your resume, it showed that you were like totally not cool in the like machine learning area. But now everybody has it on there because it's totally cool. It just goes to show how you can't predict anything except for you can use these to predict lots of things. Okay. All right. So now we have maybe like a little more complicated thing here. This was all pretty simple because it was just like these, you know, univariate functions. But now we've got two different variables coming together in this addition. So what's going to happen here? So we need to calculate what the local gradient is for this branch, and the local gradient is for this branch. So let's start with, I don't know which one I have room for. Let's do this one. So what's the local gradient for this branch? This is going to be the partial derivative of this sum with respect to this variable. What is that? So it's like, you know, x plus y equals z. The partial of z with respect to x. 1. Awesome, so easy. Addition. So there's a 1. So the local gradient's 1, and then our our upstream gradient is 0.2. So we're going to get, oh, this goes that direction. We get them both at the same time. Gave it away, dang it. Okay, so yeah, we get a 0.2 here. We get 1 times 0.2, and you can probably see really quickly that it's the same thing over here. When we take the sum, the partial of this sum with respect to this other variable, we get 1 again times the upstream gradient. So this sum is just kind of pushing back whatever is the upstream gradient here. And we've worked our way all the way back to this. So what is this value right here? What does this number right here represent? This is important. It's the whole reason why we're doing this. So it's a partial of something with respect to something. What is it? Yeah. It's the partial of f with respect to this weight, W2, at the values of W and this particular input X. Right? So cool. So that's great. So now we know the direction, or like the value of steepest ascent for this parameter W2. Again, at this point. So we're like at some point in the loss surface with respect to this data point. Okay, cool. Next, we got more addition. Oh, yes. Shoot. Now my slide better. Next, we have addition again. So it does exactly what this does. It just keeps pushing this thing back. So 0.2 again. Now we're back to right to the input. These original input nodes. So we have a multiplication of W naught and X naught, and so we know what the upstream gradient is, 0.2. Now we're just going to propagate this gradient back to W naught and X naught. So again, this is like X times, this time X times Y, 2 inputs equals Z. So for the top one, we're asking like, what's the partial of Z with respect to X? So what is that? It's the other value. So it's like, so in this particular example, it's W naught times X naught is equal to Z. So the partial of Z with respect to W naught is X naught, right? So it's that value minus 1. So that's your local gradient for the partial with respect to W naught, and then multiplied by 0.2. So that's just minus 0.2. And then the other one, it takes the other value, W naught, to multiplies by minus 2. And why is that 0.2? Yeah, that should be 0.4. That's just 0.4, right? Yeah, that's really silly. I don't know. That's an inexplicable numerical round-off error. 4.2. I don't know. Okay, before I hit the next button, what are these right here? Let's do this one. The partial W1 the partial of this product with respect to W1. Maybe minus 2 times 0.2. And then the other one is minus 3 times 0.2. Hopefully no round-off errors. What happened to all round-off errors? All round-off errors. I don't know. I'm going to have to do that. Okay, so yeah. And so let's come back. Well, we can look at it here. So again, what is this value right here? This red value, what is that? It's a partial derivative. It's the partial derivative with respect to the output, in this case F, with respect to W naught at these values. This is the partial derivative of the output F with respect to W1 at these values, and that's that. So right now that's telling us what is the direction of steepest ascent with respect to, like, you can think of this as a loss, but just with respect to this function F. And now if we wanted to update our weights in such a way that we were trying to decrease the loss function, we would then just take the negative of that and then multiply that by some small learning rate or step size, and then adjust the weights accordingly, and we'd be at a new part of our loss function, hopefully now at a lower loss because we're walking down the gradient.
So 3 of those are weights, 2 of them are not weights.
Yep.
So do you need to calculate those?
Not for updating the weights. No, you don't need to do those. But I mean, like,
Right.
you just, that's all, like, we just
Ignore that.
Yeah, that was just that part of the branch. Remember that what we're doing again is we're calculating the loss at the data points, right? So we're getting one loss per sample in our data, or like in our mini batch, and we're adding those up, right? So like, you're right that like we don't need these for updating the weights, but they're a crucial part of, like, in the forward pass, obviously getting the right values, because we're calculating the loss at a particular data point. Yeah.
For the first value, the back propagation, why do we choose 1?
Yeah, because this is the partial of f with respect to f.
Oh, okay.
Yeah.
That makes sense.
Yep. It's the easiest one to do. When in doubt, just put a 1. Yep. So like all these are partial derivatives. Each one of these is a partial derivative of f with respect to some variable in this computation. The first one is with respect to itself. And as you work back, it's just with respect to the input into that node. Right? So we worked our way all the way back to the weights. And that's what we wanted, because that's what we need to update our weights in the backpropagation algorithm. So the point of this slide here is just to say that we really, like we broke this up into, maybe like its simplest terms, or like simplest operations. So like we did when we got to this e to the minus something term, actually the whole thing. Yeah. So this whole computation right here can be thought of as that function right there, which it has a name, the sigmoid function. And so we broke it up into take your input, multiply it by -1, exponentiate it, add 1, and then take the reciprocal. But once we've done that, like, that's fine. We can also just calculate the derivative of that sigmoid function with respect to its input, and then we would have some expression like this. So instead of having to go through all of these steps, this takes this whole thing and makes it just one step, right? So we know so we have our upstream gradient 1, we have our input to the sigmoid function 1, and we can calculate this gradient again here by just taking this this gradient identity, this derivative identity. The derivative of the sigmoid with respect to its input is just 1 minus the sigmoid of that input times the sigmoid of that input. So we know what that is for the forward pass. The sigmoid at our input is 0.73. So we have 1 minus 0.73, that's the first term, 0.73, that's the second term. We get 0.2. So it's just, however you define your nodes doesn't really matter as long as you take your derivatives correctly. Because, this is giving you the same gradient here as if you'd gone through each of the individual nodes that we did before. So, and this is how this is how the frameworks, like the automatic differentiation frameworks work. They recognize more complex functions than just like these atomic ones. It sort of speeds things up, but not by a whole lot. Okay. Questions on that? All right, back propagation. So let's talk about it. So there's kinds of there's some you start to notice as you do these things, you start to notice patterns in like certain operations. So we already noticed this one with an add gate or an add node. When we're doing back propagation, it really doesn't matter what the actual values of the inputs are. We notice that when we take the partial derivative of this sum with respect to either one of the, or all of the inputs, we just get a 1. So the local gradient's a 1 times the upstream gradient. All the branches just get the upstream gradient. So you might think of the AND operation as just a distributor of the gradient. Just all the branches get that gradient. How about max? So a max operation. So we take, so this, here's a simple example. You have a 2 and a -1. You take the max of those, that's obviously 2. So what's the derivative of the max function? So what does max look like? What's the derivative of the max function? So so we say z is equal to max of like x and y. Now we want to know what's the partial of z with respect to x, what's the partial of z with respect to y. Who wants to be brave? Try it. You never took the derivative of the max function before. That's not in your calculus book inside the cover.
I guess it's 1.
There is a 1 someplace. Yeah. Yeah, there's a 1 and there's a 0. Good job getting it from that again. Yeah, there's a 1 and there's a 0. So it just depends on which one's bigger, right? So, like, if it turns out that x is greater than y, what does this look like? This is, so we were just to draw this, wherever we're at here. There's 2 dimensions here, but let's just say, I can't even draw it exactly. Yeah, let's just say this is x. So let's say like y is right here. As soon as x becomes greater than y, then what we have is just this linear function with slope 1. It's just x. As soon as x greater than y, this is just x, right? And then when x becomes less than y, they just sort of change roles, and now it's y that's doing this thing. It's just floating around. So yeah, so it's pretty simple. We just have to kind of keep track of which one's greater. So so 1, the local derivative is 1. That's the one that's for the variable that's greater. For the other one's the local derivative is 0 because it's not depending on that. For the input that's less. So 1 times the input just gives you, 1 times the upstream gradient gives you that value. 1, so just sort of passes it on to here, but then it drops it to 0 in the other branch. So it's like a router, just a router to the largest value. Any question?
So when the values are equal, when x equals y, we just assign it to y.
Yeah. So like realistically, that will never happen. Like numerically, that will never happen. That's an event of probability 0, which means it could happen, but it won't happen in your lifetime. When you're just like kind of randomly sampling, of course you can make it happen. In which case, you usually just make a choice about like you just say like the first derivative or the first argument is like the one that's going to receive the gradient, or you could choose to like split it between the two, or I don't know. You can do all kinds of things. It doesn't really matter what you do there. It's not, the derivative is not defined there. You have to just make a kind of a good choice and just stick with it, knowing that it'll never matter. Good question. Okay, max is nice. What about multiplication? How can we think about multiplication? Yeah, it's like a switch, right? It's like, it's a switch that depends on the state. So because the derivative of like the first argument, the derivative of the output or of the product with respect to the first argument is the second argument. It matters what the value here is. That isn't true for addition or for max. So these don't depend on state, but these do, and so you just got to keep track of that, and you just multiply your upstream gradient by that other value. So it's like a switcher. Yeah, switcher. It switches. That doesn't. I mean, there's nothing deep here. It's just kind of thinking through like what's going on here. Okay. So that was like in the simplest case, I guess. What backprop does. So now, something that might be a little bit more complicated is what if you have a couple of different branches coming into a node, right? So what this means is in your computation, there's at least two branches of computation that branch off from this node that are using the output from this node, right? So one's doing something with it, another branch is doing something else with it. If we're doing loss functions, like if this is computation of a loss function, they're eventually going to come back together because the whole computation has to come back to a scalar value. That's just a single scalar value is going to evaluate how we're doing on this task. But this happens all the time when these things get branched out. So the good news is this is not hard to do. It's not hard to deal with. You simply have to so you're basically going to have two upstream gradients, and you just got to add those together and pass that through the node. And the way to think about that is just the idea that that input is sort of contributing. It's not twice in the sense of multiplicative, but it's like contributing in two different ways. And so with respect to the gradient, it's got two different chances to change the slope or the gradient there. And so they add together because of the nice properties of gradients. So that's nice. That's how you deal with branches in the output. Okay, now vectorize code. So this is exactly the same. You just now have a bunch of indices to pay attention to. So everything on this is exactly the same as it was before. It's just now in your mind you have to just go, oh, I see. This is a matrix probably, or it could be a vector. And I just have to do the right matrix vector multiplication, and everything works really well as long as you have things in the right order. Which again, linear algebra there isn't something special about linear algebra that says like the matrices have to be this way or the transpose. It's just you pick a way and you stick with it. And if you change, then you get the wrong answer. So that's all. So upstream gradients. So our loss is still going to be a single scalar value. Losses always are a single scalar value. You're going to have one measure of how well we're doing. But you're now taking the gradient of that with respect to possibly many outputs. And so the partial of a scalar with respect to a vector ends up being a vector. If you're doing things in a certain way, they always have the same length or size. It's just usually, I don't know. I think we'll probably in this class kind of stick with they have the same shape as the variable with which you're doing partial derivatives, but mathematically you usually don't do it that way. You usually have it be like the transpose of output. I think in this class we end up doing it that way. But as long as as long as the right things line up with each other, you're doing it the right way. So that's a vector. And now let's say we have we know that our output's multidimensional and our input's multidimensional. So that is going to be a matrix. And the way you just think about that is like the entries in this matrix are all the partials of all the entries of z with respect to all the entries of x, right? So it's just like one of those is going to like parameterize your rows. One of those is going to parameterize your columns. And now you have this matrix of gradients. And that becomes what's known as the Jacobian. Same thing for your partial of z with respect to y. Then, to do backprop, to get your partial of the loss with respect to x, you're going to have a matrix multiplication, this partial due with respect to x. So this matrix multiplied with this vector, and so you're going to get back a vector. Again, that's right, because the loss is a scalar, and you take the partial of that with respect to a vector, you get a vector. So like everything's tracking nicely. And same thing with y, just replace what x with y. Does that make sense? Anybody like super scared of this? Like, I don't like taking lots of partial derivatives. There's really no magic to it. Like, if you really get like scared, and you're like, I don't know what to do, and the TMs aren't available, and I'm not available, which is always, then you just start taking all the partials and make sure that they like line up the right way. Be brave, try, don't be paralyzed, and just make sure, like when you're doing this multiplication, that the shapes are in such a way that like you're multiplying the right z's with the right z's here, and it will all work out the right way. We'll do an example, I think, here in a second. Oh yeah, let's take a look here. So let's think about this for a second. So let's say that we have this is our node in our computation graph. We're doing a max. By the way, the reason why we're seeing this max over and over again is because this is one of our most well-used activations, our most well-used linearities when we're doing neural networks. It's called the rectified linearity unit, or regular. It's just a max with 0. And yeah, so that's why we're seeing it over and over again. Okay, so let's say that we have like huge dimensional input, 4096, and then we're doing element-wise max with 0. So that means that we're getting an output for each of the entries of x. So we're getting a 4096 dimensional output. So what's the size of the partial of f with respect to x? Was it 4096? There's definitely 4096 in there. 4096. That's right. You're getting a matrix, right? Your outputs high dimensional. Your outputs multidimensional. Your inputs multidimensional. So you're getting a 4096 by 4096, not factorial. This is just like, whoa, that's huge, right? Because how many entries is this? Now we're really big. Because like how many entries is this? How many zeros in this number here? Yeah, like this is on the order of 16 million, right? So like, does that fit in memory easily? Especially if these are like floats. No, this doesn't fit in memory very easily. Like this very simple, stupid nonlinearity actually immediately could cause you problems because you have this great big huge matrix you're trying to store remember. So while all like the math and the algorithm is pretty simple, like you still have to pay attention to things like size here. So there's definitely ways to get around things like this. This particular pretty simple, but just know that these are big numbers. They get to be big really quickly, and that was just for one data point. Our batch size, I don't know, might have 32 or 64 or whatever. So now you got to have one of these Jacobians for each of the data points, right? So now it's even worse. So I pick a nice mini batch size like 100, which you'd never pick because it's not a power of 2. Just warning you. You'll look dumb if you pick a batch size not a power of 2. But you can multiply this easily. Like all of a sudden this becomes like a gigantic. Now you're in the billions, hundreds of millions of entries. So yeah, you're going to need something more. You have to do something different. So just know, while this is simple, you guys still pay attention to kind of to the computational aspects of this, some of the numerical or just basic resource constraints. Okay, so let's do a simple example here of backpropagation in this multidimensional situation. So we're going to do something super simple here. This is W. So our function f has two inputs, a vector x and the matrix of parameters w. And what we're going to do is we're going to multiply w times x. That's going to give us another vector. And then we're going to compute the Euclidean norm of that, the L2 norm of that. And for the square of the L2 norm. So you get so what we basically have here is we have the square, so the sum of the squares of all of the entries in the vector w times x. Okay. Now what we want to do is we want to do backpropagation with that as the output. Is that a scalar? Is the output of f a scalar? Yeah, it's a scalar. You took a matrix and a vector, multiplied them together to get a vector, and then computed this norm, the square of this norm, you're getting a scalar. So we're in good territory for this as an example, I guess. All right. Yeah. So in this example, this is how we're going to do this. W is going to be square. In this example, W is going to be 2 by 2. X is going to be 2 because it's a 4 example. Can't do anything higher than that on the board. Too hard. Okay. So it might look something like this, like our computation graph. So matrix input, vector input, multiply them together. That's a matrix vector multiplication, not just standard multiplication. And then this L2 operation. It's technically the square of the L2 norm. So okay, so let's do backpropagation here. So we're going to do this at the parameter values of W like that, and our data point X like that. So we do the forward pass. So the forward pass requires us to do the matrix vector multiplication. Trust me that it's that, although you shouldn't trust me because like the last ones were goofy. And then when I square those and add them up, I get a 0.116. Okay? So we're now going to do backpropagation. Okay. What number is going to go right here? 1. Why? Because that's the partial of f with respect to f. Good. It never changes. Okay, so now we want to backpropagate this through this operation here. It's a little more complicated because it's taking as input the vector, this two-dimensional vector. So what's L2 doing here? It's squaring each entry and adding them up. So there's we could have broken this L2 node into a couple of different operations here, right? We could have done, it takes the first entry and squares it, the second entry and squares it, and those two branches come together in an addition, and then that's the output. But we're going to do this multi-dimensionally. It's going to be great. So what we need to know what the partial is with respect to each of the partial of the output of this with respect to these two inputs. So we gave names to things over here. So the vector that is the output of W times X, we're just calling Q. And then when we apply the L2 node to this, it's F of Q, so it's just this operation right here, the sum of the squares. And then N here is only 2, so this is just Q1 squared plus Q2 squared. And this right here is just W11x1 plus W12x2. This is W21x1 plus W22x2. Okay. So let's look at this. So what we need is we need the local gradient for each of these entries. We have our upstream gradient of 1. We need the local entries of this with respect to each of these inputs, Q1 and Q2. So when we look at this is pretty simple. So if I look at this, if I just look at this part of the operation, I take the partial of this with respect to Q1. What do I get? I get 2Q1, right? And then if I take the partial with respect to Q2, what do I get? 2Q2. Yeah, these are just nice polynomials, like nice and simple. So that's what it's showing right here. These are your partials with respect to Q, I equals 1 with respect to Q1, I equals 2 with respect to Q2, 2Q1, 2Q2. So what is the gradient going to look like right here? So it's going to be, so the first entry, we're going to take our value of Q1, which is 0.22, multiply it by 2, it's going to give us 0.44 if I don't have any dumb rounding errors. And then I'm going to multiply all that by 1. So I'm going to get a 0.44, and then what am I going to get for my other value here? 0.26, multiply that by 2, 0.52, multiply by 1, 0.52. So fingers crossed, that's actually what we get. Yes! Slides didn't act up on me. Awesome. So that's our gradient at that point. Is that making sense? We did multivariate calculus by just paying attention to each entry. That's all it ever was. That's all it ever will be. If it felt really complicated in Calculus 3, that teacher just didn't make it, just didn't point out. You just did it entry by entry. You should have. It all gets a mess when you start using cross products and emergencies. Okay, good. So now we have this step. So now what is this? What is this right here? What's this red term right here? It's the gradient of our output f with respect to q. Our output of this, which is our output of our input to this, the output of that, the input to this. Cool. So we've moved the gradient back one step through that node. Okay, so now we just have this multiplication. And this follows the same rules as like the switchers, the switchers before, but it's just a little more complicated because you have more indices to pay attention to. But I promise you we can do this. So, so what we have now is we're thinking about this operation, this matrix vector multiplication. W times x equals q. So we have a vector here, so so let's think about the gradient of this output with respect to our weights. We have 4 weights. So that's going to be parameterized by I and j. I equals 1 and 2 for the rows, I equals 1 and 2 for the columns. And then k here is just the 2 different entries in our output, right? So it's just a bunch of indices to keep track of where everything's going. I mentioned that that's all linear algebra is. Yeah, that's all it is. Okay, so let's think about this. So this is what Q looks like. So let's say K is equal to 1. So we're just concentrating on the first row here. Okay. So and let's take the partial derivative of that with respect to 1, 1. Okay. So what do I get? Just look at this term here. I take the partial derivative of this row, or this entry in this row. It's not even a row. It's just one entry because this is a vector. When I take the derivative of this with respect to the partial derivative of this with respect to W11, what do I get? X1. All this fancy notation over here says is when K is equal to 1 and I is equal to 1, then this becomes a 1. And the only time, and let's see, am I doing this right? Oh, and J is equal to 1, right. So, okay, sorry, I sort of said that wrong. So K is equal to 1 and I is equal to 1. So this is 1 equals 1. So this like funny notation here is Dirac delta function, or just like the indicator function. So it's a 1 when these two things are equal to each other and a 0 otherwise. Just notation for a simple idea. So it's called the indicator function to indicate when these are equal. And then, so this is the 1. So what do we have left over here? We have the j is equal to 1, so we get an x1. So this term actually ends up being x1. You know, it looks pretty complicated. It's just x1. Now let's do this. Yeah, so let's now do this partial, the same row with respect to w1, 2. What do we get looking at this? x2. And it's the same story here. X equals is, or sorry, k is equal to 1, I is equal to 1, so this is a 1, and then j is equal to 2, so we get an x2. And the reason for this thing right here is if I take the partial, so when k is equal to 1, but let's say that I is equal to 2, right? So this is Q1, and there's no W2 in this, right? So k is equal to 1, I is equal to 2. That means these are not equal, so this is a 0. So you just get a 0. So that's why that funny notation is there, is to kind of, again, keep track of which row you're on because of the way that all this works. And if we just start now, we set k equal to 2, and we start working through our partial derivatives with respect to W21 and W22, you're just going to get, again, x1 and x2. So we have this is our tensor, a third order tensor, because we have 3 indices. But for each of the q's, we're getting a matrix, right? So if we just fix k, like q, so this is partial q1, we're getting an entry for each of the four values of ij, and that's giving us a matrix. Okay. So that's our local gradient. And now our upstream, we need to be able to bring our upstream gradient into this. And this is where we have this. You don't see it in here, but because this is multi-dimensional, we have all of these entries kind of contributing this. We have a sum over all of these partials. It's basically all of these. These are all the paths that through which our weights can affect the output. And this is again just applications of the chain rule and the product rule. We pass through all of the q's, right? So there's only 2 in this case, but we're working our way through all the q's to get back to the final one. So that's why there's that sum there. We already calculated what these gradients were. We just calculated what this gradient is. So for k equals 1 or 2, so in this case I. So this is only ever 0 when k is equal to I. So in that case, you're just getting 2qi times xj. So this is our partial f with respect to wij, this term right here. And again, this is a matrix, right? Because this is a scalar and this is a matrix. So we're getting out a matrix of the same size as this, and it's parameterized by the same indices I and j. Cool. So that's good. Having that, we can go through and we can calculate some. So this was okay. So remember, this was our local gradient, and these were our upstream gradients. Each of these, right? This and this. So now we can do whatever we need to. And notice all we have here is the QIs and the XJs. Let's see. Yeah. The way this, sorry. Yeah, this is, so let me just say it one more time. These terms right here, this right here represents all of our upstream gradients. This represents all of the local gradients, in the right order, in the right paths. We calculated these, and it just turns out to simplify to that. So we can calculate what our partial of f is with respect to w in that way, and we just start going through all the terms, taking our q's from here, because there's not a gradient in there, right? Taking our q's from there, and our x's from here. That's the switching. Remember, this is multiplication, so there's no w's in there. We're using the values of x. We can go through and calculate it, and it turns out to be those values. And I actually did check those. Those are right. I did check the other ones, obviously. I was change those to the point. Not the numerical round numbers. Okay, does that make sense?
Can we just calculate the 0.88?
What do you mean when you say just calculate? Because that's what we just did. We just calculated. Like we did. So it's, oh, you mean like, oh, sure, yeah. So I see what you're saying. Got it. So, so this entry right here, 1, 1, right? So that's the 0.088. That's the partial of f with respect to W11. Okay? So that's going to be 2 times Q1 times X1. Okay? Q1 is, let's see, Q1 is no, Q1 is 0.22, right? Times, so it's 0.22, that's Q1, times 2, that's 0.44, which is the thing right there, but don't get it confused. That's 0.44, and then times X1, which is 0.2. So that gives you a 0.88, but then because it's a 0.2, you move the decimal point 1, and you get a 0.088. And so on, right? So this one right here is partial of f with respect to W2, 1. So this would be 2 times Q2 times X1. And Q2 is 0.26, and X1 again is 0.2. So you have 0.26 times 2 is 0.52 times 0.2 is 0.104. And yeah, that makes sense. We just keep everywhere you look, there are a set of indices, and you just take those indices and you plug them into this formula over here, and then just find the relevant terms somewhere in the computation graph. Yeah.
Sorry, I think I might be missing something.
Sure.
Where does this summation operator come from when we're computing the overall gradient?
Yeah. So this is there are two. Think of this as as producing two branches. So for the input. So for W and X, this is producing two outputs. The upper entry there 0.22 and the lower entry 0.26, right? So just kind of glibly we said that the way that you combine those, like multiple branches coming into a node through backpropagation, is just adding those terms up, which is what's happening here, right? This is just a sum over each of those terms. Like the K is an index over the entries of Q. This comes about just through the properties of so just chain rule and the product rule, and yeah, like I don't know, just basic calculus identities of how gradients behave through these multiple pathways. Again, because this is a scalar, right? So like, because this is a scalar, like, think of it this way, like dimensional analysis, like this has to also end up, so because this f is a scalar, this has to be a scalar, so, that's not going to be the right way to tell you that. Let's see. Well, it is true. That's not the right way to tell you that. So, yeah, that's like a sufficient condition. I don't know. This is just these are just properties of these multivariate gradients. And if you have, let's see. Let me think about it for just a second, because there's like a way I want to explain it, but for some reason it's not coming to mind. So it'll come to mind here in just like a couple minutes. But anyways, but again, like just going back to that previous slide, we have the sums over all the branches coming back into this node. And again, like each of these branches has an opportunity to affect the end output f. And so what I'm trying to come up with in my mind is like the property that makes it add. And I'm not coming up with it right away. I'll come up with it in a second. Okay. So, okay, right. So we did that for W. So again, now we have, again, like to your point, now we have the gradients, the partial derivatives of f with respect to the weights. We can now just update the weights, right? We can take the negative of that and update our weights, and that would, we'll multiply by learning rate, update our weights. That will move us to a new part in the a new spot in the parameter space, update our loss function. We just do this all over again. You don't necessarily have to compute the partial with respect to x, but we could, because we're so good at math. Oh yeah, and this is just writing right here. Like this is like the vectorized way, the multivariate way of writing down this expression right here. That's like the full Jacobian of f with respect to w is 2 times the vector q times the transpose of the vector x. And that's giving you a matrix. So the q is, our vectors are always columns. We do this outer product. We do this times the transpose is now the product giving us a matrix. And it just gives you that value there. Question?
So when we find the gradient of f with respect to w, all we have to do at that point is we just take the negative of that, which would be the not the greatest ascent, but the greatest descent.
Greatest descent.
And then
The negative multiplied by some learning rate or step size, like how far you want to step in that direction. But yeah.
And then right after that, then we plug those values back into the weight.
Not those values. You're taking that negative gradient and you're adding it. So that negative gradient times the step size, and you're adding it to your current set of weights. So like that vector up there in green. So it's that minus some learning rate lambda times that matrix in red, and that's your update. That's moving the parameters in the direction of the steepest descent.
Oh, okay.
Got it?
I'm seeing that. Yeah.
All right. One person sees it. We're well on our way. Okay. Yeah. We could do this next one too, but we're running out of time, I think. All of this might be the end. Okay. Yeah. So we have 5 minutes left. Let me just skip over that. I mean, it's exactly the same process. Just keep track of all the terms, and you can get the gradient of f with respect to the inputs x. Okay. So what does all this mean? Well, what this means is we have a way. So if we have a computation graph that's connecting us from our inputs to our output, we have kind of an algorithm, a notion of how to compute, how to do back propagation. This is just kind of pseudocode here, but it's something like the following. Our forward pass, we just need to start from the beginning of our computation graph and work our way through all the computations. So there's the computation graph. It's a graph because it's like we know what our inputs are, and then we know how they're connected together through nodes and how those nodes are connected, and they kind of work their way through to the end. So we have some notion of ordering of those computations. This topologically sort of means that like we're working through the operations in such a way that we never ask for an operation before a previous operation is being done. So if we do this, we just you can think of it like in a pseudocode sort of way of like for each of these gates or each of these operations, there's some way of computing the forward the forward path, or like for that node, the output of that node. And we work our way all the way through. And if there's a loss function or is a computation for a loss function, then the final value coming out of this forward pass is our loss. Backward, we just want to work our way exactly backward through this computation. It's the same thing. There's some notion of how to do the backward pass for each of the nodes. And when we get back to it, then we just have our gradients for all the inputs. Of course, doing back propagation, we only really care about it for our weights, but we'll use it. Like you'll see when we start doing some of the ways of sort of trying to understand what convolutional neural networks are doing. like how they're making decisions from the pixels in the image, we actually used ideas of like the gradient with respect to the inputs to get some promotion of that. Well, that's coming up in a couple weeks. But in general, we're just using fat propagation to update the loss function, the parameters of the loss function. So this might seem very complicated. In fact, if you started the homework, it might feel very complicated because this is what you're doing. You're basically doing these for all kinds of things. Here's a particular example for multiplication. And the important part here is that when you do the forward pass, you're storing certain value that you need for when you do the backwards pass. So like the multiplication on the switcher, you have your inputs, you calculate your output, but then you store, this is just in Python notation, you're storing the values of x and y, and then you need those because those are your local gradients that you multiply with your upstream gradients to move backwards. So notice that like this backward, like in this particular example, the forward takes the inputs and the backward pass takes the current upstream gradient and then just updates that for whatever this particular gradient, in this case multiply, and returns those to the previous one, and then that just keeps going. So the good news here is like once you go through, once you do all this awful homework so that you know how this works, then you just turn to the frameworks that exist for doing neural network computation, graph building, and training, and all this stuff is already there for you. All these layers, these are all nodes in your graph. The forward pass, it knows how to do the forward pass, it knows how to do the backward pass. That's all it's doing when you're training these neural networks. You're putting this big computation graph together, and then this thing just knows, however you put the nodes together, it just knows how to do the forward and backward pass, and just does it for you over and over and over again until you've made $1 million doing something. Yeah, that's what we're doing in our assignment. So we're doing this for fairly simple models, which is good. And yeah, getting some practice in how that will do. So good luck with all that. We'll talk more about this. We'll talk about activation functions and more on Thursday.